Okay, we are recording. So, welcome to week 7. This is the grand finale of the course. I meant to put my face up on this broadcast as well, but I guess we'll do that next time. Yeah, this is the grand finale. We are today going to learn all about networking, and basically, through the course we've learned how to do loops, how to do recursion, how to do functions. We test on classes. We did a little drawing. We've done all sorts of stuff, and in my mind, this is where things start to get real world. We did CSV. That's also pretty real world, but today we're basically going to learn how to spell networking. We're also going to learn how the internet works. So if you guys have ever used the internet like we are right now, today's lesson is going to be all about that and how to build real-time networked applications. So lesson 6 last week, we was all about testing and debugging, and we had a test assignment where I gave you guys a broken Caesar cipher. And I guess I'll explain that for Marina, who wasn't here. The Caesar cipher is a way of encrypting encrypting a message, and I gave as an assignment a way to take a Caesar cipher that was kind of working but not entirely working, and to have you kind of understand what's broken with it. Similarly, there was a debugging assignment where I gave out a buggy version of Google Maps, the navigation, and said, hey, can you guys sit down and given the source code, find the bug, as opposed to the testing assignment where you didn't have the source code and you had to find the bug. So did anyone attempt these assignments, or are we still waiting on that? Not just yet?
Not yet.
Not yet. Okay. Well, I guess when we get to it, we can do it. And also, while we're getting started, anyone have any questions from prior material we want to go over before we dig into it? Or should we just dig in? All right, we're digging in. So today we're going to learn how to build a chat server and a chat client. So basically, if you ever use WhatsApp or Google Hangouts or Facebook Messenger, it's the same core ideas are used in all those messaging services. And the server component, that's the bit that lives on some powerful machine in a data somewhere. And then the client, that's the part that your user actually uses. So you'll see that when you build a network system, you need to have at least 2 pieces in order for everything to run. So let me switch screens, and we're going to take a look at what a, let's see. Ooh, this might be a little challenging because I don't think I have a good way of sharing both terminals at once. We're going to try this though. Okay, so here is my screen. Ooh, I killed it. So here's my terminal, and I'm going to try splitting it for you guys. I forgot that I was going to have to do this, so let me look up one command real quick so we can split this terminal into multiple pieces, because I've got a limitation on my machine where I can only share one window at a time. I can't share the whole screen. So here we go. So Control B and quote. Control B and %. So you guys should see now I've got these 3 panes, and how do I move around them? Control B and arrow. Okay, Control B and up. So you'll see here that I've got an example for you, a server and a client file. And by the way, is this all coming? Is plainly visible to you guys? All 3 windows?
Yep. Yeah.
Yeah, good. So we've got a client and a server file. I won't show them to you just yet because this is going to be your homework. But what you'll want to do is you start the server running, and then you come down into another window, and you run the client, and the client says, what is your name? Well, my name is David. This is hello, David. And, oh, sorry, actually, I'm loaded up the wrong version of this. But the idea being that, oops, that I can open up another one. Says name is Bob. Bob comes back. But I'm actually gonna keep going a little bit further. In this example, this is actually not the completed assignment. This is an earlier version where you send one message and it says hello, your name back. But in this case, the users are not able to chat to each other. So I'm actually going to jump up to a different example. I'm going to show you guys how we're going to chat with each other. Trust me, guys, I made so many different chat programs when I was trying to figure out the best way to teach you guys. I'm a little bit confused about which was the one that I got 100% working. I think it might be this one. Yeah, because sockets and networking, a lot of people actually make it really difficult to work with, and so I was trying to find the best set of tools where we could do sockets in a really simple way. And I think this is the simple one. Okay, here we go. So you see up here in the top, we're running the server, and the server says, hey, I'm running on this address, and actually I'm going to pause. Have any of you guys seen a number like this before? Does anyone know the name for something like this? Anyone at all?
Looks like an IP address.
There we go, IP address. That's the first part's an IP address, but what's the second part called? Do you know?
Localhost.
Okay, close. So this one, so localhost. Well, we're jumping ahead a little bit, but localhost is a name meaning the current computer, and localhost is the human word for this number. This number is kind of the computer address for localhost, meaning the current computer. And so this on the back end is called a port. And I realized that in my slides we actually don't talk about a port, so it's good that we're talking about it now. But essentially, yes, it's running the server on the current computer, localhost, colon means on the port 8089. So port, you can think of a IP address as being like a phone number, and the port is kind of like an extension. So your computer is a big office building. You know, we dial into that building, and then we do extension 8089. That's where the server is running, and then these clients connect on this current computer on 53976, and likewise this guy 53982. And so when I say hi from, I don't know, hi from David, send, and then it shows up over here on the left side. We can say hi from Bob, you know, what's up? So again, this one, a little bit better of an example, but you notice that it's not actually sending a username, it's sending this ugly IP address and a port for you. And it's funny because I didn't mean for you guys to see all these different variants in the demo. I meant to go right to the right one, but then I forgot which one the right one is. So you guys are going to see all my different iterations of chat systems. I think this one, if I remember correctly, works really nicely, except when you stop it, it dies in like a ball of fire. What's interesting about programming is that there's like a million ways to shoot yourself in the foot. Let's see. Okay, so here we go. So this I think will be the final version that I show you guys, where again we've got the server running up top, and we've got two clients running on the bottom. And this time I can say, hey, this is David, and then I can say, hey, this is Bob, and now I can say, what's your favorite color? And I can say over here, I can say definitely blue. And you can see that these messages are passed back and forth between the clients, and we can have as many people as we want in here. We could even, let's see here, go in again, I can Python client, and I can say George, and I can say, sorry, I'm late. Oh, sorry, you guys can't see George. I opened George in a different window. But I guess that helps prove the point. Bwahaha, you can't see me. So George is off screen right now, and I'm typing in, and you can see that we have at least 3 parties here in this chat. So I'm going to hit the pause button. Does anyone have questions or comments on this example so far?
How are you able to open up different chat windows? Like, do you just have to get different people to open up like Python client.py, or how do you like get everybody into the same server?
Yeah, that's right. So at the moment, you have to have your users run Python client.py. So we aren't building a really pretty user interface for this. In the bonus assignment, we do something that's more like a real, like user-friendly application. But for the core assignment today, we're just going to learn how to do it using client.py. Does that make sense? Yeah.
Yeah.
Okay. And then likewise, I think your question was how do you get people to connect in? Is that right as well?
Yeah.
So I guess here's another thing is that actually we might be able to do this because we're all on the same home network. Is that I could give you guys the client code and I could run the server and then we could all speak over the network. But right now, I'm going to change screens. This code that we have here, it always connects to localhost. I'm not sure. Should I show you this one? Okay, I'm going to show you the basic listening code, and can you guys see that? Okay.
Yeah.
Yeah. So this is the key line right here, line 5. We're going to go into this in more detail during the class, but you'll see right now it's always saying localhost 8765. And then I forgot the connection code. This is really the one you care about. So this is what a client would run. So if you put, like, let's say we were building a chat app on your phone, then on your phone, this right here, localhost 8675, obviously you wouldn't be connecting to localhost if you're from your phone. Your phone isn't running the chat server. The chat server is somewhere else. So you would probably come into here, you'd say like, marina.com/chat or something like that, or like, chat.marina.com, and then you would be running your chat server here, and when you run this code, it would go find that server at that address. Does that make sense so far?
Yeah, kind of. I guess it's like part of the lesson, I guess, right? So.
Yeah. So it will be part of the lesson. Any other questions on what we've seen so far? No? Great. Well, yeah, I think something that I'll tell you guys is that a really cool moment for me was I was in a programming class and we were asked to build AOL Instant Messenger, and it included like a buddy list and sending files and everything, and like to get that to work was amazing. Like to fire that up and say, wow, like I built a crappy version of this program that I grew up with. That was cool. So I think hopefully you guys will get something out of this class as well, because I think chat is just neat. Right. So the 4 things that we'll learn as a part of learning how to build a chat app are basically how the internet works, what the heck the network stack or the protocol stack is. We're going to learn about these 2 different types of networking and how they apply to how you might develop a game or a website. And the final thing is WebSockets. That's a type of networking that we'll be doing today. We're using WebSockets to build our chat application. So at a high level, the internet essentially, and this might be crazy to you guys, the internet is like it's run by a set of microscopic carrier pigeons. And what I mean by that is that when you send a carrier pigeon to carry your message to the other side, you don't actually know if it got there, right? It's not like a phone call where on the phone, we pick up the phone, we say hello, the other person says, yes, I can hear you, right? We get a response back right away. But with the internet, at its lowest level, it's really about sending these little tiny pouches of data, we call them packets, and we hope that the pigeon makes it to the other side. And I think this is fascinating. And particularly when you realize that we've set up these network connections that connect all the major countries in the world to this global network. And yet, the mechanism is not as tidy as we like to think. Because again, if you look at the map, let's say we wanted to connect from let's say, Mexico to Japan, right? Or maybe Mexico to India, even better. So if we go from Mexico, clearly we need to make a few hops before we get to India. India doesn't have a direct connection from Mexico. So the way this works is essentially is that each little hub here is taking packets from the source and routing it one stop closer to the destination. So if we're going from Mexico to India, looks like we go Mexico to, what's a close link? It's kind of hard because this is all on top of each other. But I don't know, maybe we go through Europe and then Europe hops over to India or something like that. But in reality, it's more like, if I go to yahoo.com, I'm in Vancouver and Yahoo's in California, I'll probably hop through Washington State and Oregon and then maybe California and go to Yahoo. And each hop, again, the reason I use a carrier pigeon metaphor is that the pigeon itself, so to speak, it's really just this packet of data. You really send this packet of data out there, and it's marked like to and from, and then you're trusting essentially all these other nodes on the way to like push it one step in the right direction. So to me, this is really fascinating. This idea that all of our modern communications are based on this kind of one-way idea. We kind of, it's almost we're shooting data out of a cannon. It goes off, and we just hope that it gets there. So we're going to learn more about that mechanism as we go forward. So did this make any sense to you guys so far, or am I just rambling like a crazy man?
Makes sense.
Makes sense?
It's really interesting, actually. I had no idea that's how it worked.
Yeah, it's totally how it works. You're basically you're trusting all the other members of the network to be trustworthy. You're trusting them with your data. You're saying, hey man, here's a packet. Please send it. Please send it one hop closer to the destination.
What happens if a hub goes down? Is there do they know how to reroute, or does that information get lost?
Ooh, that's a great question. Well, we're going to learn how to deal with those kinds of situations during this class. But by default, if your pigeon, if your precious little packet is going hop, hop, and then one of the nodes that it hits crashes, let's say, your data is lost. That packet, boom, it's like you've never sent it. So clearly, if you want to get work done on the internet, you're going to have a way to deal with those situations, because failures are going to happen, right? And you can't afford to, like, let's say, go out of business or lose the customer's information just because one packet in Germany got lost. Cool?
Cool.
All right. So this is something that I want to walk you through. So this is like an actual example of, like, when you type in google.com in your web browser, what's actually going on. So there's all these different steps, and I tried to give it to you in terms of like the technical lingo, and then like the technical explanation, and then maybe kind of a human level thing. So it's like following the human level thing. We type in www.google.com, and that becomes this IP address. Likewise, human terms. Where is Google's headquarters? The packets then come in. This command we have of get google.com root. This is like this slash means the home page. A lot of people don't know that when it's like http://www.google.com/. This slash is actually a really important part of that URL. It often gets overlooked, but essentially the command that your computer sends to the internet or to Google is get me this IP address, the home page. This slash means the home page. And so this gets chopped up into packets and sent to the nearest computer close to the destination. Again, which is, in carrier pigeons terms, carrier pigeons, you're headed to 1600 Amphitheater Parkway, Mountain View, California, right? Where this address kind of corresponds with that, google.com. Next step, the packets, make a couple hops through the internet. Eventually, Google receives them. I received a carrier pigeon. Who's it from? Google receives the packages, the ASYNC packets, assembles back into the whole message, get 172.217.3.164/. Because if this is a really big message, it won't be able to fit in one packet. right? If you're watching a movie on Netflix, then that movie definitely doesn't fit in one packet. That's millions, probably billions actually, of packets that float across the internet. So the receiver has to have some way of putting these packets back together and understand what the message is. And then, given that you've gotten the message, you need Google in this case would construct a response and then chop the response up into packets and then send it back to me. So it's like, okay, send this new carrier pigeon back to David K. So does that make sense to you guys? I guess I should do a check for understanding. Okay, so actually, here's a great question. Has anyone ever bought a domain name before?
Yes.
Yes. Trina is resisting because she knows she's going to be put on the spot. So Trina, when you buy a domain name, who are you buying it from?
Some host, what are they called again? Domain name host.
Okay, some domain name host. And then when you buy it and you go to your website, let's say you buy Trina.com. You buy Trina.com, then you go to Trina.com. What do you see on that page normally?
Well, I can't recall what it says now. It's really, it really has no information there. I think it has some message. I don't know what it is.
So I guess what I'm driving at is that when you first buy a domain, well, okay, first of all, if no one has a domain and you go to Trina.com, you get an error. It's like, hey, this page doesn't exist. In fact, we can try that right now. Let's play with that. So let's say we go to, well, Trina.com is probably taken, right? You can probably say, yeah, I can say like blah blah blah.com. I'll probably just make up some.
Oh, it's the orange juice.
The orange juice. Oh, here. Okay. Chrome right now doesn't let me go to a garbage site. Here, hold on. LADS.com. There we go. So see this? LASDFJ.com service DNS address cannot be found. So what this is saying is, hey, I asked where is, what's the IP address that corresponds with this domain name? And there is no domain that's registered to that address. So I just want to point that out. There essentially, you can think of DNS, it's like a shared phone book of what all the names that correspond with all the IPs are. Or in Python terms, you can think of it as a big dictionary, right? Where you given a domain name, you map that to an IP address. Cool? Cool. All right. So, yeah. Oh, yeah. So we spoke about IP address and packets already. IP address is like a phone number. Packets are those small little packets that you give to the little package you give to a carrier pigeon. TCP versus UDP. This is a classic thing, and I think Andre might have been exposed to this because he's a gamer. Andre, hey, can you tell us anything about TCP versus UDP? Hello? Okay, might be having microphone issues. So we're going to go to the next one, and then Andre's going to let us know when he's working. If I had to stereotype TCP versus UDP, TCP is slower, more deliberate, more reliable, much like the mastermind Gus Fring from Breaking Bad. UDP is when speed and performance are more important than anything, and you don't mind if the guy makes a couple mistakes or loses some of your data. So just like we spoke about before, what happens if something breaks on the internet, and does your packet get lost? And the answer is TCP has come up with a way to handle that. That if the data doesn't get to the destination, TCP will send it again. UDP rolls fast and loose. You only live once, and if the data gets lost, you move on. Right? You pretend it never happened. So to just break that down into a table, TCP, this is amazing, by the way. TCP these are, yeah, two different ways of transmitting data over the internet. And most people in industry end up using TCP because if you lose any of your data, TCP figures it out and resends the data. Likewise, TCP guarantees that your data always arrives in order. And why is that important? Well, if you go back and look at this chart, what if we send from Mexico, we send some packets through Europe and some packets through South Africa on the way to India? Then it's not guaranteed that if we send packets 1 and 2 through Europe and 3 and 4 through South Africa, that they'll arrive in India in the order 1, 2, 3, 4. It might be that the order ends up being 1, 3, 4, 2 or something like that if there's some sort of network issue on the way. So TCP basically it introduces overhead. Again, it's slower than UDP, but the data will always arrive in order. And it's basically, you can think of it as like underneath the covers. Basically, UDP is eventually like it doesn't give you much over what the internet does by default. UDP is basically, you can think of it as like raw internet protocol. While TCP essentially is this kind of extended higher level version where it says, okay, hey, we know that most people want to deal with data loss. We know that most people want their data in order. So why don't we sacrifice the performance of UDP and we'll just delay and resend and delay and resend until the stuff gets there. And when the stuff gets there, then we move on. So,
David?
Yeah.
At what level who chooses to send TCP versus UDP?
Great question. So that's a question for, well, okay, so we're going to talk about that more in the next section, but I'll say this. Essentially, it's the programmer, right? If you're designing the system, if you're saying, hey, I'm going to build an app to manage patient records, or I'm going to build an app to, I don't know, stream video to my grandma, or whatever it is. Anytime you sit down and say, okay, we're going to build this thing, and it's gonna use a network, then you've got the decision to go TCP UDP.
Can you give an example of what would use UDP?
Yeah. So that's coming up. So hold your horses. TCP versus UDP. On the left, these are examples from the gaming world, we have World of Warcraft. This is a game which is about walking around in dungeons and killing dragons and things like that, but and chatting with your friends and all that. But the combat, it's not very time sensitive, right? It's as long as you make your move within about a second or so, then what do you call it? Then you're good, right? And then things kind of have looser tolerances here. Compare that with Call of Duty. Call of Duty, it's a very precise game. What matters, within like one frame on the TV is very important. So you basically want the greatest performance possible in a game like Call of Duty. You want the greatest, lowest level of latency, right? And so in this case, Call of Duty actually uses UDP to minimize latency, and then World of Warcraft says, latency is okay. Latency meaning a delay. World of Warcraft says latency is okay. We'd rather take the consistency and the in order and integrity of TCP. So I'm going to give you a couple more examples. Oh, actually, I'm going to ask you this one. Firefox, Chrome, and Safari. Do you think they're primarily about TCP or about UDP?
UDP?
Why is that?
Chrome? I don't know. Chrome's just faster than all of them. So I'm guessing UDP, but I could be wrong.
So it's not UDP. So it's TCP. So these applications, they're all using HTTP. HTTP is a TCP protocol, and so I think the reason is that their primary job is to get a document and make sure they got the whole document. You know what I mean? Like an HTML page is referred to as a document. So when you go to Google.com, you want the greatest concern is, did we get all of it, and did it get garbled? I'm sending my credit card. Did I screw up? Those correctness concerns are really, really important in these browsers. So these are all TCP based. You can see UDP come up in some cases. We'll talk about this in a second, but it's primarily TCP. All right, here's another question. WhatsApp. Do you think WhatsApp, would you use TCP or UDP? Let's say just the text messaging part of WhatsApp. Andre, you want to take a stab at this? Oh, is his mic still broken? I think his mic is broken. All right, ladies, TCP or UDP for WhatsApp?
Andre just said TCP.
Oh, he said TCP.
But
Oh, he put it in the
okay,
chat. Okay, TCP. What's that?
I'm wondering because now that it's encrypted and all these packets have to go into these specialized encrypted packages, I don't know. I'm guessing TCP has just so much more capability than UDP. I'm gonna say TCP then.
Okay, TCP is correct. Yeah, anytime that it's like you don't want to deal with data loss, you want to use TCP, and provided that any kind of delays are okay. And you guys are exactly right. TCP in this case. What about FaceTime? TCP or UDP?
Because it has to go performance, right? And I guess a few frames of missed connection is okay, as we've all seen. So yeah, UDP.
Yep, exactly. You guys are right. This is a UDP application because if it were TCP based, then let's say there's some data loss. There's data loss on the line. Then TCP says, wait up, I'm not going to give you the next frame. I'm going to wait until that missing frame gets here, and then I'm going to give you the data. And when I say give you, I mean like the rest of the application, right? Like the part that renders the video to the screen and all that. So you're right. So if this were TCP, it would be weird. Like I think, was it Skype? There was one chat voice chat application that once upon a time used TCP, and you would get these funny like fast forwarding events where you were like there'd be lag and you wouldn't hear them, and then you'd hear them like play back all of their audio at once. So you hear them go blah, 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 and then they'd be back. Yeah. Anyway, so you're right. Most of the time that you do voice and video streaming, it's UDP for that reason, that you lose a couple frames and then move on. The protocol stack. Oh, actually, any further questions on TCP UDP so far?
How do you figure out which one it is? Like, do you just have to Google it and find out, or is it somewhat obvious just because of, like, the functionality of things?
So, I mean, I grew up playing a lot of video games as a kid, and I would say that you can probably figure it out just by kind of playing the game. But I would say, okay, there's three ways you can do it. One, you can play the game and kind of know how games tend to be when they're played one way or the other, and kind of try and observe. You basically want to observe how it deals with data loss on the network. Like in a shooter game, classically what happens in a shooter game is you'll get people who teleport. Like if someone teleports in a game, it's more of a UDP kind of thing to happen. Anyway, so one is to observe the game behavior. The second way is to Google it and ask the guys what they use. And the third way is there's this tool called Wireshark. There are alternatives, but the best well-known one is called Wireshark. And do you have a screenshot here? Yeah. So Wireshark basically gives you Wireshark gives you this interface where you can watch network traffic and you can investigate what it's doing. And so if you were ever in doubt, you can fire up Wireshark and look at the network traffic, the packets coming out of your computer, and it'll be able to tell right away, aha, this is TCP. Got it?
Yeah, thank you.
So let's see, protocol stack. So this is a question that comes up in a lot of programming interviews. Like, all right, tell me about what are the 4 layers of the protocol stack? Or I think often people say 5 layers. This one has been removed. And there's a lot of alphabet soup in here, as you can see. HTTP, FTP, TCP. I don't know. I think that should be UDP, not UPD. Maybe they're messing with us. IP, ARP, DSL, ISDN, Ethernet. Has anyone heard any of these words before, or is there any you haven't heard before? Anything you want to point out?
Not the
Yeah.
ICMP or the IS.
Oh, I think Andre's mic is back.
Can you hear me?
Yeah, we can.
Okay. It's really low though, right?
No, it's pretty good. I think it's perfect.
Okay. Yeah. I don't know a lot in this.
Yeah, you want to point out one that you do know?
ARP?
ARP, what's that one?
Oh, that I do know.
Yeah, point one that you do.
Ethernet.
Ethernet, what does Ethernet do?
It basically connects your computer to the router.
Yep, like local networking, right?
Yeah.
Yeah, cool. All right, Marina, can you point one out that you know?
Well, I've heard of the names, but I don't really know exactly what they do. So like the POP or HTTP.
Yeah,
Yeah, I've heard of them, but I don't know what they do exactly.
got it. What context have you heard these in?
I think whenever you set up your internet connection or yeah, something like that. Like if you have like a new computer.
Yeah.
Yeah. But
Yeah,
that's pretty much it.
No, that's fine. That's fine. So POP and IMAP, these are both email protocols. I think it's Post Office Protocol, I think, and Internet Mail Application Protocol. So these are both, if you ever set up your email, you'll probably, and SMTP as well, Simple Mail Transfer Protocol or Send Mail Transfer Protocol. So these are all email related on the right side. So if you use Outlook or Thunderbird or something, you'll need to punch in your email settings using these guys. And then HTTP, that's what we use when we browse the web. This is probably the most widely used protocol these days. And then SSL, you might, anytime you see the lock on the web browser bar, like you're inputting your credit card, that's for encrypting the channel, secure sockets layer. FTP, you might share some files with your friends over FTP. That's less common these days, but back in the late 90s, early 2000s, people had FTP sites where they put files up. TCP and UDP, we just learned. We see that that's a layer lower level than this stuff, meaning like HTTP is built in terms of TCP, right? So each layer is kind of using the layer beneath it. And I guess I'll explain that next slide. But again, IP, Internet Protocol, ARP, this is for resolving local machines in your local network. Hey, who has this MAC address? DSL and ISDN, these are for doing different types of like telephone-based networking. Or sorry, ISDN is more, I believe, fiber. But if we translate this into terms that we might be more familiar with, and this is a bit of a crude metaphor, so I think my fellow computer scientists might disapprove. But you might think that at the top level, the higher up we get, the closer we are to human concerns. The lower level we get, the more it is kind of like nitty-gritty electronics type stuff and software. So we might say, okay, we've got the message SOS, which maps to in Morse code, dot 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 dash 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 dot dot dot, which maps to in a digital signal 000111000, which maps to a electromagnetic radio wave, which again doesn't look quite like this waveform. I couldn't find the right waveform, didn't make it in time. But the idea being that we have this top layer, which is like maybe a string of text in this case. The layer below that, the Morse code. The layer below that is this digital 1-0 representation. The layer below that is this analog representation that actually goes through the air to the destination. And this mapping here of this left, like, well, HTTP sends TCP messages. TCP messages are made of IP messages. IP messages are really passed over Ethernet between computer to computer. And each layer is a little bit different than the one above, but you can see how there's a mapping between them. Any questions on this so far?
So like for each layer, it uses one of each basically? Is that how it works?
Yeah, basically, yeah. So we can look at an example of that, where let's say we go to google.com and we run the GET request. If we do a GET request on google.com, like if we go to google.com in Firefox, then that's HTTP is our application layer protocol, which is using TCP as the transport layer protocol, which is using IP as a network layer protocol, which may be using Ethernet as the link protocol, which is as a link layer, which is using IEEE 802.3u as a physical layer. So to put that into more visual language, HTTPs and Firefox, TCP/IP and Ethernet are more kind of binary concerns in the code, and then IEEE 802.3u that describes this network jack and how electricity flows through this network jack. So again, you guys will probably never have to worry about anything below. Okay, you'll definitely never have to worry anything below TCP. In most cases, you'll probably just use TCP and just worry about whatever's up here. But I'm giving you guys this information just so if someone says something about one of these lower levels, so you have some idea that, oh, okay, this is really what's going on. There's this mapping to a mapping to a mapping, and electricity gets sent. Electricity gets sent in and out of this port. Does that make sense?
Yeah.
Yeah. Okay. So, by the way, has anyone had any internet epiphanies so far? Are they thinking about TCP/UDP or this carrier pigeon idea? Anyone want to share any breakthroughs or confusion so far?
Well, I don't know. I just had like a thought about like globally, are there places where it's slower then? Because like if you think that you're saying that you have to island hop, right? Or I mean, like you have to hop through different continents for your data package to get to places, right? So is there like places where I don't know, is there like an inequality in like internet access, I guess?
Yeah, for sure. There's an inequality. They like I spent about a month in Kenya, which should be this guy right here, and internet out there was not so good. And one of the reasons for that is that I believe, if I recall correctly, man, I can't remember which country they were going out through. I think some of it was going over to India and then over, and some of it I think was going up to some part of North Africa and then out. So like browsing American sites from Kenya, not a lot of fun, right? I mean, you can think about it in terms of like, well, if we in our homes need to be buying an internet connection with a certain amount of bandwidth, well, these guys who are providing bandwidth around the world, they've got to be being paid by someone else too, right? Like a lot of the ways, a lot of the time, we're paying Verizon or Telus or Novus or one of those, and they end up buying deals with big providers at more of the national level, right? Or sometimes they just lay a bunch of fiber and they enter a barter deal. Something that's really interesting that I don't know a lot about is that the big guys in the fiber business and the internet business, they actually will sign what they call a peering agreement. Is that if I'm really big and you're really big, then we'll agree not to pay each other for bandwidth, but to give each other bandwidth for free. So anyway, I might be going into too much detail, but long story short, it costs money to move the data around, and so there will be some areas that are not as well connected as others, for sure. Quick trivia fact, for many years the best connected place in the world was South Korea. I don't know if that is still the case, but I think it's pretty funny to see these little oddities, like South Korea is really good. What's the other one? Not Macedonia.
Is
I
this
forget
an
it.
official map of how these packets are transferred?
So this map is more about how much data goes from place to place. It's less about where the links actually are. If we want actually a map of internet lines or backlines, that's good. There is actually, here we go. This is going to be something like a more realistic map. So this is the United States. So if we zoom in, you can see that Dallas is a major internet hub. St. Louis, Kansas City, also on the main line. DC, obviously for military purposes. New York, which fans out internationally. What else we got? Looks like Chicago. Yeah, Chicago makes sense because there are major financial centers. A lot of financial transactions that fly back and forth between Chicago and New York. Seattle apparently is the big one up in the northwest, San Fran. So this is the United States. If we go and look at the world, then again, this is probably not entirely up to date, but yeah, you've got these orange guys, which are the major hubs, and they connect with other hubs directly.
So I have a question.
Yep.
So how should I word this? So say we're in North America, we're building for something that we know what our kind of like our internet speed is, so we're going to build a TCP. But then do we have to keep in mind other countries then who may not, I don't know the difference in speed and reliability between TCP and UDP that would there actually need to be, would we need to write the same thing in UDP because some countries may not have the same speed?
Yeah, that's a great question. I think at the end of the day, it's more about is it okay to slow down your application in the case of data loss? That's the key question. It's like if it's okay to wait for data, then TCP is fine. If it's not okay to wait, then you want to look at UDP. And yeah, I guess you're right. If you're developing something for sub-Saharan Africa, then your presumptions about how long you'll need to wait in the case of data loss may be wrong. It may be that you're waiting 5 times longer than expected, and that becomes not tenable for your users, right? I think so your question is, but to answer your question though, would UDP actually fix the problem? Not always, right? Like basically, like in the case that you're using UDP, you need to either do one of two things. Like in the case of Call of Duty, they might just throw away all that information that got errored out in the case of UDP. But let's say you're implementing, I don't know, health records or financial transactions using UDP. Well, you'd still have to send the data because all the data needs to get there. And now you have to write this custom code to do the retry. Basically you have to figure out when the data didn't make it there and send more carrier pigeons. So to answer your question, you can roll a UDP implementation if you're targeting Africa, but first of all, will it really solve your problem? Second of all, is it worth the effort? And I think those are the questions. So I would say, what's that?
Sorry, is the main difference of decision based on the speed? Because it's not. I don't understand reliability. I'm only seeing speed as really the deciding factor.
Well, it's the delay thing. It's like, okay, so to come back to FaceTime. FaceTime's a great example. So in FaceTime, if we did TCP, then if there's a network outage, then we just wait. And so I see a frozen image of you for however long, and then I get a bunch of images of you that are late. And the thing though is that if that's how it works, then you're almost always going to be late. You're almost always going to be behind. So yeah, so I would say performance is probably the biggest. Wow. Or here's another thing. Here's a really interesting question. Let's say we go to Google Music, right? Is it better to make Google Music using TCP or using UDP?
We definitely want TCP.
Oh man, I couldn't get that. The TCP. Is that right?
Yeah.
And why?
You want it all to be. You want the music to sound as how the artist originally had it recorded.
Okay. Well, what if I went to that's a livecoding.tv. Okay. This is a live streaming website, and there are programmers who stream their programming sessions on here. And this guy's doing a live broadcast right now, so we can fire it up, and I can watch this dude's live broadcast of him programming. Is this a good place to do TCP or UDP?
I guess in this case it doesn't really matter because each frame, doesn't matter too much. You're not losing really important data, so UDP then.
So yeah, it's a really great question. It's a really, really great question. I think it depends on your perspective. It's like, well, if it's more okay for me to go behind schedule than to like, wait, how important is it for me to have up to date information, right? If up to date information is the most important thing, then UDP, drop a couple frames. But if it's more important for me to watch the whole broadcast, as the author intended, so to speak, then it's TCP. And so I think that in most cases there's an obvious answer, and I would argue that for live video, it's a little bit more. It's a little more vague. It's harder to tell, in my opinion.
So then so once again, if it's really down to performance, then at one point, once everyone gets something like Google Fiber, it'll all be TCP then, wouldn't it?
I mean, you would think so, but FaceTime still works really funny if you do it on TCP, even if everyone has a great connection. Like, no matter how great we make the connections, there's always data loss. No matter what we do, it's almost like every biological system you ever look at, there's always some part of it that's in failure at any given time.
Okay, so I'm just trying to like clear up my confusion a little bit. So
yeah.
Is UDP versus TCP, is that dependent on the program or the machine that you are building, or is it more like the connection between between countries, or like the bandwidth?
It's more application dependent, I would argue.
Okay.
I would say if you're building a video app, it makes more sense to use UDP. Like video chat, if you're building video chat, just use UDP.
Okay, so you're like, as a programmer, decide if you're using TCP or UDP?
Yes, that's what yes.
Okay.
Yes. So I'd say yeah. Generally speaking, what kind of app are you doing? Do it like that. There may be some crazy special edge cases, but I would say it's almost always application driven. Yeah. Well, yeah. Okay, great. So now we're getting to the application part. So if we look at this guy, WebSockets are a type. It's a way of doing TCP sockets. You might argue that actually, yeah, it's this application layer protocol that's built on top of either TCP sockets or UDP sockets. It's a different variant of WebSockets in either case. And this was originally developed so you could do sockets in the browser. For many years, Firefox, Chrome, Safari, Internet Explorer could not do sockets. Sockets meaning real-time communication. And Python and many other languages have implementations of the standard WebSockets. And I found that after surveying, as you saw, like 5 different ways of building the chat application today, I found that this WebSockets approach was the easiest one for you guys to learn. So you will need to install this outside library, WebSockets. If you click this link, you'll go to the web page. Oh, I really should have linked to this page, which is their documentation. So if you get stuck, you can click around here and read about how it works. But really, in here, the slideshow, you should have everything you need to know.
Hey, just to be clear,
what's that, man?
When you do the pip install WebSockets,
yeah,
that automatically gives you access to everything that you clicked in GitHub, right? So I can import anything from there, and it knows to import, compliance.
Yeah.
I can do import compliance or.
Yeah, basically. Yeah, I mean, well, technically, it's a little more complicated than that. Technically, this setup.py file says what you're actually getting. So if you look in here, where is it? I'm actually really confused about which part of it actually tells you what to do. It might, actually, I think it's this one right here. Yeah. So this right here says the directory WebSockets is being exported as import WebSockets, right? Like this name here corresponds with this name here. So if you go back and like thus this one here, so this is the directory that you actually get. If you import example, if you import compliance, if you import docs, you won't actually be able to access those. This is the one you're getting. But to answer your question, when you do pip install, you're pip installing this whole folder of Python code. And this would apply for other stuff. Like before we did Cocos2D for Palm, and let's see here. I'll find the GitHub repo just so we can browse it. La, la, la. Okay, yeah, here we go. So likewise, if you do pip install Cocos from the games example, you're pip installing this directory here, this Cocos thing with all these Python files. So if you get curious, you can just click around and see how these things work. Like in WebSocket, you could say, you know, how does server work? Right? You can look around here.
Gotcha. Thanks.
Good. Cool. So yeah, so you'll need to install WebSockets. Just run pip install WebSockets on your command line. In your Python code, you use it with import WebSockets, and then I'll just show you a couple snippets. Sending data, WebSocket.send hello world. Receiving data, receive, and you get a message back. But can you guys tell me if there's anything strange going on in these code snippets? Maybe something you haven't seen before?
I'm not seeing any of this, so.
Await, maybe?
Await, exactly. Await. What the heck would await mean?
Does it mean kind of like pending? Kind of like it's it's like you're sending a code through and then it's going through a process and it might or might not get there, like you said about data loss. Is it connected or?
Kind of, yeah. So in this case, await. In this case, WebSocket.send. I guess this is more complicated than I thought it would be to explain. In the good old days of networking programming, when we say WebSocket.send, our program would wait here on this line. Like, let me try and find it in a no. Yeah, okay. So if this were, let's say, 10 years ago, the way all programs would be written is that when we get to line 3, let's pretend these asyncs and awaits are not here. Let's just pretend those are not here for now. We get to, or actually, I'll type it up. I'll type it up because this will be a little bit more precise. Okay. Share the other screen. So okay, so if this were the good old days, then we would say something like socket.send hello world, and then we would say socket.send or or print I sent the message. So does this make sense so far, guys? Yeah? Can you accept what these lines or guess what these lines might do? I'll aim it at Marina right now. Marina, do you feel very 100% comfortable with this code? You can say no. It's okay.
Okay, well, I kind of understand because I'm just like trying to understand because you're saying that socket.send is saying send this message called hello world, and then right after that it'll print out I sent the message, so it'll print it out on your screen, right? Not the other person.
Yeah, that's right. So prints out I sent the message on your screen, not theirs. Yeah.
Yeah, I think I get it.
Okay. So what happens on line 3?
I don't understand what socket.send does.
Yeah, I guess that's my trouble too.
Okay, great, no problem. So we're gonna learn this in 1 second how to make this thing. But essentially what you do is you basically say socket equal to WebSockets, and you could be importing here, import WebSockets. Actually, I'm gonna call this old sockets. I'm gonna call this old sockets just to differentiate, because I want to show you the new way that WebSockets uses. But you'd say something like this: connect localhost 1234, and now you got a socket. So this socket thing it's a network connection. It's either it's a TCP or it's a UDP connection to to the other computer. So given this connection, we want to send this message, hello world. Does that make any sense? Or is that terrible?
So like the dot send is like a function?
Exactly. That's right.
Okay.
Yeah, just like back in Pong, I think we had like self dot position equal to 1. That was like a variable inside of the like paddle. And I think we might have had paddle dot bounce or something like that. I can't remember exactly what we did, but we had this idea. Anytime you can put a variable or you can put a function inside of this other thing. This was covered in the discussion on classes, which I think was mainly week 4 and 5, I think. Yeah, I'm a little bit fuzzy on which week it was. But if this is confusing, this is the idea of class. Class is basically when you can have this thing, a paddle, a socket, a Barbie, that embeds other variables or other functions inside of it. So in this case, the send is a function, but that send lives inside of socket. That's what's going on here.
Mm-hmm.
Does this make sense now? Or can you actually explain this to me now? 5, 6, 7. One line at a time. What's 5 doing?
Okay, so I think 5, you're building the function, so socket, and then you're saying, okay, so at a higher level, socket is equal to old socket dot connect. So I'm guessing dot connect is also kind of a function.
That's right.
To localhost, and then you're saying, okay, within socket, within kind of taking the line 5 socket, you say socket dot send hello world. So it's another function within socket, and then you're saying, okay, send that message hello world, and then right after you send it, it'll print on your own screen, I sent the message.
That's right. That's 100% right. Good work.
Okay.
So now I'm going to show you the new way. Okay. New way. Pi. So in the new way, it looks a lot like this. Call it WebSockets. WebSocks. Go to websocks.com. Buy all the socks you need. All right. So okay. All right. Now I'm gonna leave this unchanged. I'm gonna leave this unchanged for 1 second, and I'm gonna ask you: does this program on the right behave exactly the same way as the one on the left, or is there a subtle difference? Oh, here. I'll do this. So in the old way, I'll make it more visual. In the old way, let's say we have, let's say the connect function returns a old socket with the address as a parameter. And we have old socket who has a function called send message. Actually, I should make this real syntax, you guys. Not gonna do pseudocode. And then I would say self connection equal to connect address. And I'd say something like self connection send message. Okay. On the left, that would be the old way, and then I'll just call this new socket. Well, I'll call it WebSocket just to be consistent. WebSocket. WebSocket. And then, okay. Okay, great. So I'm going to ask Andre for this one. So Andre, if this, basically we're using the exact same code here on the bottom, 16, 17, 18. Those are exactly the same between both cases. The only thing we've changed is this line right here, line 12. Can you hazard a guess as to whether program on the right and program on the left will be different, and how?
The one on the right is going to be probably a little bit slower.
Okay, why is it going to be slower?
Because it's async, not sync.
Not sure.
I don't know what async is. Is it not syncing?
Okay, so here, basically, yeah, this is. What you guess?
No, I'm wondering if it's not syncing, but I've never heard of the word async before. So.
Okay, so async stands for asynchronous, and essentially what's going on here is. Man, this is a little bit tricky to explain, but basically what's going on here is that this task might take a long time. This send might take a long time. Like, for example, if we're sending this to Kenya, this will take a long, long, long time to finish. If we're sending it next door, it'll finish really quickly. And so here's the difference, is that the difference between these two is that in 17, or rather in the old way, when we do socket.send without async here, then we wait at line 17 to send to Kenya. We don't go to line 18 until it's reached Kenya.
Yeah, but how do we know? So we're waiting for Kenya to tell us that it reached Kenya?
Yes. If I was presuming it's a TCP socket. So, a great question, by the way. But the old way of doing networking, like this is just a programming thing. Like networking didn't change, but programmers changed the way they looked at networking over the last like 5-10 years, and I would say probably 5 to 8 years actually. But the key insight is that this line 17 is what they call a blocking call. And so the idea is, hey guys, stop everything. We're gonna wait right here. We're gonna finish. Here's the key idea. We must finish this task before moving on. That's the core idea of this left side. But here's the thing. Over here, on the right, if we use async, we only need to start the task before we move on.
Okay, so does that mean that like while it's starting to send and the hello world is starting to send while it's pending, it might as well go ahead and print out I sent the message?
Exactly. That's exactly right.
Oh. So that's why it's asynchronous.
Yes.
Okay.
Yes. Because it'll finish some other time, and then by default we won't know. By default we'll just keep doing our own thing. But it's off executing while we're doing something else. So this might seem really confusing, but put it this way. Computers are actually getting better and better and better at doing multiple things at once, right? Like you heard about multi-core. Each core essentially is one actor in your computer, one thread in your computer. And so the better that you can ask the computer to do multiple tasks at once, the more you'll be able to get done. Or, for example, let's say you are sending stuff to Kenya. Well, maybe you've got 6 people in your chat room, and you don't want the Kenyan guy to slow down your Canadians who all have fiber optic internet, right? And so if you have synchronous communications, you might have one laggy guy slowing down everyone else. But if you have asynchronous communications, then you can let the laggy guy get the message when he gets the message, and you just keep sending messages to everyone else. So checking comfort level here. Trina, how are you feeling?
I'm good, but I thought that you said there was no way that we would know if the carrier pigeon would receive the message or not.
Yeah.
How is the old sockets able to wait?
Well, okay, so same question as Andre then. So you're right. IP doesn't know. TCP knows. So if we come back to the diagram right here, basically the TCP guys realize that IP is a pain in the butt, because every time you lose data, you've got to figure out that you've lost it. And they realized that everyone was having that same challenge with IP. So they said, hey guys, what if we just built the standard data loss code and we just put it in one place so everyone can just use the standard data loss stuff and they don't have to worry about data loss anymore. They can worry about other things. So that's where TCP came from. So they have mechanisms in there basically where they number all the carrier pigeons, and they ask the guy like, hey, did you get number 3? And he's like, what do you mean? I got 1, 2, and 4. Like, oh, well then we better send you number 3 again.
Oh, so UDP doesn't packet them, doesn't number them, but TCP
Well,
does.
no. Well, I think UDP also has a numbering system, but like they don't really act on it in the same way. Like UDP is, they call it fire and forget. You basically, it's like you point a fire hose at the other guy and say, all right, here we go. And TCP is more bidirectional. It's more like, hey man, did you get this? Did you get the other thing? You did? Okay, great. Let's move on. So TCP is actually going to be less network efficient. Like you were talking about earlier, like would you ever rewrite your code? I guess technically yes. There is that overhead from doing TCP, and you could avoid that with using UDP. But again, it gets really tricky because like anytime you do error correction, there's some level of overhead. Because you know overhead meaning like if I'm just saying 1, 2, 3, 4, or I don't know, read my credit card number to you, 4, 1, 1, 1, 2, 3, 9. If I read my credit card to you and I don't check that you've got it correctly, you might have an error. So it's a little slower for me to just read it to you, and then I say, can you read it back? And that's a way for us to check for data loss.
So is TCP also, you know, one of those really old chat rooms we used to ping you? So is that kind of like pinging?
I believe there is a pinging built in. So in sockets, there's this idea of something called a keep alive, or it's also known as a heartbeat. And the basic idea here is that you ping the server. Yeah, okay, there we go. TCP keep alives are an optional feature, default to off. So yeah, so TCP does include a pinging in the protocol, but there are other types of pinging. But the basic idea of pinging is, yeah, it's like, is this person still connected? Are they asleep? Yeah.
Okay.
Cool. So let's come back to the code. Yeah, so just to drill this in one last time, is that, again, this is the key line. We must finish this task before moving on, versus we must start the task before moving on. And just like Marina said, the one on the right, in many cases, might say, I sent the message, before the message is really finished sending. Right? It might be just barely started sending, it might be halfway, it might be almost done, it might be done, but we don't know anymore. And so that sounds like a bad thing, but it turns out that in most cases you actually don't want for the Kenyan guy to receive your message before you go do some other stuff. Like, we want our computers to be basically doing stuff all the time. Like, here's an example. Let's go back to WhatsApp. So if we look at WhatsApp, let's say WhatsApp, as we said, is TCP, and let's say you're chatting with your buddy in Kenya, and you hit send, and then it says sending. Well, the ability for your phone to show you the spinning wheel while it's sending and it hasn't been received, to me, that's an indicator that these guys are using async. Because if they were using sync, the computer in your iPhone wouldn't be able to draw on the screen in order to show the activity indicator. Like, that takes some computing cycles to move the screen around. And so if you hog the thread then by running the networking, and you're all synchronized, you say, wait, don't do anything until you finish sending the message, then you can't type on the keyboard, you can't scroll up and down, you can't go back to chats, you can't spin the wheel. You can't do anything. So does that make sense, guys?
So, DK, how do I know when it sends then? So based on the code you wrote in wherever you wrote it?
In the terminal, yeah.
Yeah, in the terminal?
Yeah.
So the async, we don't know when that's going to ping us back, but how do I catch that?
Okay, so that's a great question. Marina and Trina, did you guys understand that question?
Yeah.
Yeah.
Yeah? Okay, so you're right, because on the left, when we send it, when we get to the next line, That's our pin doc. Like getting to the next line, okay, it's done. Over here, we get to the next line, and we've got no idea. So I would say there's a couple different strategies, but essentially, I'm going to show you two strategies. Here's the main one. The main one, like the iconic one. So you have this function you call callback over here, and basically right here on the bottom, you would say all done. And so over here, you would say something like def on message completed, taking I don't know. Oh yeah, I can do true. And then so, all right. So in this case, guys, do you see the difference? Well, here's a good one. You say result equal to that callback. Something like that. I'm hearing a whole lot of nothing. So let's have someone puzzle through this. Marina, puzzle through this with me.
Oh, okay. Well, okay, I'm just like really not sure about how to connect lines 12 to 15 and connecting it to 17 to 21 because like there's nothing that references back and forth between the two. So
Okay, so you're right. So in this case, let's I'm pretending that here. I'm pretending over here WebSockets.connect. I'm pretending that this is what it does. The WebSockets connect gives us this WebSocket thing, which is this object here. So essentially, this line here, we're getting a WebSocket, and the WebSocket that's this thing here, this socket that has these. Oh, that's cool that I can click there. I realized I was clicking on the wrong screen. So you've got so you got the socket here, and socket send. That's this function here, right? And then this callback. That's this on message completed right there. So that's the other link. It's basically first link. This connect. That's this. Is creating this guy, and we're calling send, which is this, and then we're passing in on message completed, which is this, to this parameter here. Should I go? Is that good? Questions on that? No?
I'm just trying to piece it together in my mind, but so how do you connect callback and on message completed? Like how do you like? I'm just having troubles like in my mind like trying to connect the two because is one like a function or something? Or?
Yeah. So on message completed is a function. Callback is a variable. But you notice that right here on line 15, we're treating callback the variable like a function by giving it the parentheses. See this? So what's going on here is that we can deduce callback the variable must be a function because we're giving it these parentheses here. Right? Are you with me so far?
Yeah.
Okay. Because it
Okay.
has parentheses, it's got to be a function. That's the only way that we use parentheses like that. So that's a function. So let's look at send and see what send put in as a callback. Send, all right, well, the message is message. And self, that's just an automatic thing in classes. So the third thing is the callback. That's this guy. What's this guy? I think there was an epiphany there.
Oh, okay. Okay, now I kind of get it now. Okay, it's kind of coming back to me. So, I think in that class where we talk about self and init, I guess like that order really matters, right? For async def send and then self comma message callback, you're referencing it back to socket.send hello world on message completed, right?
Yes,
So
yes,
is
yes.
that I think I see the message, or I mean the connection between it then, because that order matters, right? So the message is kind of corresponding to hello world, and then callback is corresponding to on message completed.
That's right. That's all right. Yes.
Okay. I that part now I get, but need to figure out the other part, I guess.
Okay. Well, just trace it through. Now let's just pretend that this is all the old way. Read this code as if it's all the old way now, and see if you can follow it.
Hmm.
So we start here, right? And you here, guys. I'm gonna make it a little taller so you guys can see the whole thing all at once. There you go.
I guess it's going. I mean, like, um, it's different, I guess, because I think of everything backwards. Like the stuff that you have at the bottom, I think of first because that's more like,
Top level.
yeah,
Okay,
exactly.
that's fine. That's fine.
Yeah,
We'll put it on the
but
top. It doesn't matter to me.
oh, okay.
Like technically Python will want it on the bottom, but I'm gonna put it on
Uh-huh.
the top to make it easier.
Okay. Okay. So I get the general gist of like what it's trying to do and the pieces of it and what it references, and so I kind of understand the general gist of the code. But running through each line is kind of difficult, I guess. But it makes sense at a higher level to me. So.
Okay, so higher level, but not the details. I want to check
Mhm.
in. Andre and Trina, how are the high level and the low level for you guys?
I think I'm okay on both.
Okay, Trina?
I'm just trying to figure out how success is called upon. So once it's looking for the callback, and then so the function send is looking for the callback, then it sees, okay, the callback is on message completed. So then when it gets to on message completed, then I don't, at this point, I guess I don't understand the definition of success yet.
Is that more clear?
Successful failure. Okay. Yes. Okay. So then okay. Now I get it.
Cool. So Trina, I want you to step through this with me so that Marina can understand the low level details. So walk me through the whole program starting at line 5. We're going to pretend. Give me your best Python interpreter impression. So starting at line 5, what do we do?
Well, we're assigning this socket this WebSockets connect. This part I'm not very too familiar with because I have to play with that first. But this WebSockets connect, I guess, is from this WebSockets that we're importing. So it's doing this thing where it's going to connect to WebSockets.
Right, and then
with this localhost.
And in our case, I drew these two lines as kind of a mock of what's actually going on inside of WebSockets. This is basically our version of what's going on in WebSockets Connect. So what's this one doing? Because this is the next line.
So it wants to connect to an address, and so you've now identified that it's looking for that one address, which is now localhost 1234.
Right, good. So how do we know what, like, so that's creating a WebSocket. Where do we actually create it? Like, what's the next line from here?
Next line from...
After line 11, where do we go?
Line 7 is where I'm, because we've called upon the address. We've called upon the WebSockets function and we've returned the address. So now we're satisfied with that function. So that's where we're going to line 7 now.
So not quite. So I just want to point out, if you want to go all the way down, technically this init is firing, right? Because anytime we create an instance of WebSocket, the init is executed using these parameters. So technically speaking, the next line is line 15, or 14 depending on how you count it, 14, 15, because you've got to set these things inside of WebSocket. And I just want to be super 100% explicit because Marina missed a class on where we went over OO, and I think that'll be helpful. So
is that a class I missed as well?
Oh, you might have missed that as well. So I guess you guys are both benefiting. So
yeah, because I don't remember ever seeing init. So
okay, let's hand it off then. Hey, Andre, pick it up, buddy. So we're at line 11. Where do we go?
All right, so as you said, we go to the init and we assign the address and the connection.
Okay, and then where are we assigning them to?
We're assigning them to the object that we created on line 11, which then wraps back to line 5.
Okay, and then so line 5. So sorry. So in terms of line 5, what did we just assign here on 1516?
An address and a connection. Wait,
Okay.
yeah, an address and a connection for the object that is socket. Oh, you're saying that what actual address? Or
No, yeah. So no, you're on the right track. I just want to be 100% explicit for the girls. So basically, these two things are now populated, Marina and Trina. So by running lines 1920, now if we say socket.address, we're going to get back this localhost 1234, and if we do socket.connection, we'll have some sort of connection object in here. Does that make sense? Can you see how line 21, 22 are linked to 7 to 10?
Yes.
Yeah.
Marina, yeah?
Yeah.
Okay. So great. So we finished that. We're back on line 5. We finished line 5. What happens now? Andre.
we're going to line 7,
Okay.
and we're going to send our first message.
Great.
Hello world.
Okay, we're sending hello world. So
And also, okay, let's go to the send now, the socket.send, which is the async. So it's going to be like a multitasking function. So this will also be running as we move forward.
So let's ignore the async right now. I'm gonna delete it. Let's pretend that's not there, because I think this understanding will be the same, but I think it'll be easier this way. So let's pretend it's no async.
Okay, so it goes into this, and it says success or failure equals self.connection.send message. We're expecting like a true-false Boolean statement there. And then we send that true or false into the callback, but callback is pulling from the onMessage completed. So it's actually onMessage completed, and then the Boolean statement, which goes to the line 22. And then we're just saying if the send was accepted, we print out message sent successfully, else it prints out error sending message. Currently how we're doing it, we wait until this finishes though, before we print out line 8.
Yes, that's right. That's right. So Marina, did that make sense? Where did we lose you?
I think the success. So is success is it like a built-in thing, or it's like if you put if success, then that means that's almost like saying true? Or
Yeah.
like where does
Yeah,
how
so-
does it know that?
So this is classic Python. Which when anytime you have if, you have basically you can have a true, or you can have a false, or you can have something that evaluates to true or false.
Okay, so like in this case, like somehow like success is attributed to true?
Well, maybe. I mean, it's a variable, right? We could have called this x, right? I could call it, yeah, I'll call this x. If x, I could say or result,
Mm-hmm.
right? So I just thought that x isn't a very helpful name. Result isn't a super helpful name. Success is decent.
Mm-hmm.
But yeah, but essentially, yeah, we don't know. It could be true, it could be false. So if it is a success, print true. Print message sent successfully. Otherwise, print that. So basically, yeah, we're like, over here on 19. I'm kind of hinting that this is a Boolean by saying that.
Okay, but like I mean, so how does like the program know that means like that it's sent kind of thing? That's the disconnect I have, because like you can label it anything you want, but you just need to know if it actually went through or not, right? And I guess I just know that if you put true um, in Python, it means it knows that it's true, right? But then if you put success or X or whatever, you can label it whatever. But how does it know that it's actually a success?
Okay, yeah. So this is a question of symbol evaluation. So let me pull up the shell again, and then we can go over this. Oh, by the way, does anyone have to go soon? Because we are over time. Do we have a little bit more time, Andre?
I have all the time in the world for you.
Great, thanks.
And you guys.
Marina and Trina, you guys are good for a little bit longer?
Yeah. Yeah.
Yeah? Okay. So let me open up the shell. Okay. So if we go into here. So, okay, so here's an example. True. True is true. False is false. If true, print yippee. Else, print so sad. Okay? We get yippee. We know this. If I say x is equal to true, then we can do the same thing. If x, print yippee, else, print so sad. We get yippee.
Wait, why are you always getting yippee? Why are you always getting true statements?
Okay. Let's do it again. Oh, here, I'll put this in a function so I don't have to keep typing it. Def, happy or sad, taking an x. If x, print yippee, else, print so sad. Okay, happy or sad on x, yippee. Y is false, happy or sad on y, so sad. Good so far, Marina?
Why did it automatically print yippee though when you didn't even put in something for X?
I had right here.
I can kind of explain that because I know it, let's say if it was x equals 2, and then if we did if x equals 4, we know that's a false statement because 2 doesn't equal 4. But what we kind of do is simplify it. So it's instead if 2 equals 4 is if false, and then we do whatever it is. So the whatever goes in front of if is always like a true or false. It's always a Boolean or a 0 or a 1.
Exactly. You can do this.
It just we're so used to seeing it this way, if 2 equals or x equals 4, but that can be simplified to a true or false statement.
Oh, I think it was because I didn't think David put in any variable and it was still coming up.
Yeah. No, I think she missed this line right here where I assigned the x.
Oh.
I thought there was something before when you just put true equals yippee and then
here.
yippee.
Yeah, I just said oh, is this the one you guys had trouble with?
Yeah, like how did yippee just come out?
Well, because if true.
But then you didn't put anything and then it just came out yippee.
Well, okay, so the way it works, So essentially it becomes if this thing is equal to true. That's
Yeah, it almost seems like you put enter.
Yeah, so
then it
this
shows
is
up true.
this is really what it's asking. So it's like if false, print I don't know, go Trump, right? And it doesn't run. Why is it running? I just told it to do it. If true, print not voting this year.
Yeah, see, it automatically always assumes true then?
No, the true is always true, and false is always false. So
But then how come it printed out it's a statement only if it's true, but not if it's false?
okay, because basically the way the if statement works, you say if whatever I put here is equal to true, then run the rest of the thing. So in this case, false is not equal to true, so it doesn't run. True is equal to true, so it runs.
If true equals blank, then true? Like, I just see you press enter, so I just don't understand what that part, how that comes.
No, this is just how the if statement works. The definition of the if statement is if blank, run the thing, right? Like if whatever I put right of if is true, then you run everything in the body, right? And I can even write that as body. If blank, run me, right? And in this case, if you hand it true, true is true.
I guess I understand true is true and true or false equals true, but it's just that you didn't pass anything through, so I don't understand why it printed.
You didn't pass anything through. Are you talking about the parameter here? Like, is this not passing anything through? Is that what you're saying?
Yeah, it doesn't seem like you're passing anything through.
Well, I mean, yeah, I mean, it's kind of like saying, all right, here, but what if I say if 4 is greater than 1? So am I passing something through here?
Yes.
What am I passing through?
Well, you're putting in something that can be answered true or false.
Something that evaluates to true or false.
Yeah.
Evaluates to. So see this? 4 greater than 1, it evaluates to true. 4 greater than 5, evaluates to false. True, evaluates to true. False, evaluates to false.
Okay, I guess that's just awkward, but I'll have to remember that. Then how come when you put if false, it's in print? But then here false is false.
Well, yeah, false is false because look, okay, but false is equal to false is true. Right? So if I said if false is equal to false, I can print logic works. If false, print voting for Trump.
Okay.
Marina, how are you feeling?
I think I understand, but I guess I was just confused with the success or failure thing because nowhere did we define what success was, I guess.
Well, okay, you're right. It's right here. It's defined off screen. There's some other thing where we have this connection send where this is kind of a black box. Like I didn't want to actually implement all the code for all the sockets because that would just take a long time. So basically, I'm just implying here that this is a Boolean based on.
Oh, okay. So like, is there like a built-in thing here going on? Where
Yeah. Basically, in this case, you can think of this connection thing as a built-in. It's a black box that we didn't do. I mean, technically speaking, this WebSocket, the real WebSocket, doesn't look exactly like this. It looks pretty much like this. This is kind of a mock version, but when you deal with the real system, you would have something like this. You would probably be like import connect from connection import connection, and you'd probably end up with something like this, like connection of address. And so we have this thing called connection send that we'd have to go look in this file to see how it works.
Oh, okay.
So this is what's going on with that. Is that this connection is a black box. It's coming from somewhere else.
Okay. I understand.
And so so this was the leap of faith that I was asking you to take. That yes, this function does return this success or failure.
Okay.
Okay. So now, is everyone comfortable with if success now, knowing that could be true or false?
Yeah.
Yeah. Okay. Excellent. So let's tie it all back around. So we just stepped through an example of what would happen. Oh, by the way, I wanna clap it off for you guys, because getting comfortable with all those concepts takes a lot of mental gymnastics. But the final thing, so originally this thing said async. And we realized pretty quickly that if this thing is async, then I sent the message might actually complete before socket send has completed. And so in the case that this is async, on message completed, this gets called, it's very likely that in the case of async, we call socket send, we say I sent the message, and then later on we get this message sent successfully printed out. Does that make sense, guys? If this is async, this is off doing its own thing while we do our own thing over here, right? We say send the thing and print I sent the message, but then when the message gets to Kenya and comes back, we get this success back, and then we fire the callback, and then it prints out message sent successfully.
So you may get, if you may have sent 5 messages and got, I sent the message, and then this message sent successfully comes back in random times.
Yes, exactly. That's right. It'll be random times.
Mm-hmm. So it'd be nice to be able to let the user know which message was sent successfully.
Right. So what you might do is you might change it. You might say something like the callback sends the message and the success or failure. And you could say something like message sent successfully, and maybe you put the message right in here. And you can say error sending message, and then you can put the message in here. Do you see that, Trina?
Yeah.
Yeah. Cool. So we just did an async mode, and now I'm going to show you guys something that might make you angry. What happens in this case?
Okay.
Are you going to let us know what await means?
You can ask, but take a guess first. What does await mean? I'll give you a hint. You know enough right now where you can take a very educated guess. Go for it, Marina. I see you're on the brink.
I feel like it kind of like conflicts a little bit with like async.
Okay, yeah. Tell me about that.
Okay, so like from what I sort of guessed about await, it sounds like await is something where, you send something and, it's like almost like pending, and it's just I think it's a little bit like the concept itself is a bit closer to TCP, and then the async is a bit closer to UDP, I think, because async is more like just independent of everything else, everybody else who's connected in on this server, but await is kind of like dependent on everything clearing up and sending first, it seems like. But I don't know exactly what await as a function does for this. And then in combination with async. Okay. Does it make sure that So like, given the fact that the entire system is asynchronous, meaning that every computer and every person is independently functioning, does it mean that when you put await, it means that you'll be able to see that your message is sending or receiving? It's, I don't know, I think I kind of get it, where it's like, as a server, like on a server level, everybody is independent, but then each person's computer is more functioning to make sure that everything is completed. That, I don't even know if that really makes sense or if I'm communicating it properly, but
No, I love the thoughts. You're dancing. You made some incredible points. Sounds like you're not quite reaching the final answer just yet.
okay.
And so I want to hand it over to either Trina or Andre if they have any ideas about how to nail this one. Trina, you feeling bold?
I'm just, no, I'm just
No.
looking to see how this, it's awaiting on this, the socket.send, so I'm just seeing where socket.send needs this await feature.
How about Andre? You got some insight? Oh, maybe his microphone isn't working again.
No, it's
Oh,
working.
it's good. Oh, okay, there we go.
Yep. Hopefully. Okay.
Yeah.
I really don't know.
All right, guys. I'm going to spoil the secret for you guys. When we don't have this, we are in async mode. But if we put await in there, it's just like we're going back to the old way. It's exactly the same. So like, I can't find the, oh, here we go, old socket. This whole old socket, where we must finish the task before moving on, if we use await, it's the same rule. This start the task becomes we must finish the task before moving on. So just changing this one little word, if we do it without, we say, oh, this is async, okay, so as soon as I start, then just come back to here and keep going. But if we say await, then we have to go here, and then we wait for the connection send, and then we wait to finish the callback, and then we come out. So what's cool about async await is that now you have easy control over whether you want to sit around and wait for things, or whether you want them to just go and do their own thing.
So await just like trumps async altogether?
Basically, yes. I mean, in short, they're designed to be a pair, and that async says, hey, I'm going to take some time. By default, you probably don't want to wait for me. And then await is like, no, I insist. I'll wait for you.
But okay. So the only way for async to work is if you don't have a wait.
Yeah, basically, yeah. And then again, by default, you don't have a wait. Okay? Everything's just going to go async on its own. But if you ever are, again, if you insist, you say, no, it's definitely got to finish first, you add a wait, and now your program will just sit around waiting.
Are await and async out of the socket import?
Great question. They are not. They're actually built into Python.
So I can use that for any of my regular programs.
That's right. I waited to drop this bomb on you guys until now because it's a pretty advanced concept, and I didn't think that you would be as prepared for it as you are now. And I think that sockets are a natural opportunity to think about this async idea. So hopefully this is sinking in for you guys a little bit.
So how about async? Is that built into Python too, or is that like part of the WebSocket?
No, async await, they're both part of Python. They were added pretty recently. Added maybe 6 months or a year ago. Pretty recent. Yeah, this is a funny fact. Async await, this style of doing asynchronous stuff, that syntax, that style was developed at Microsoft, which is pretty funny because a lot of us like to hate on Microsoft, but no, they do some good stuff, and async await I think is one of the better things. Okay, any questions on async await, guys? No? All right. So sorry that we're over. I am going to jump ahead and just show you in the slides. I've got the detail for the sending, for the receiving, and there's that await thing, right? And then I got snippets for listening for connections and making connections. I'm fast forwarding through this. Well, yeah, I'm fast forwarding through this because I think it's more important to talk about the homework, but actually I will pause. I'll say, do you guys want to ask questions about this kind of stuff? Because I am going to give you a, what do you call it? A scaffolding that has this stuff already built in. But here, no, actually, we'll pause. We'll pause for a quick second. So what's going on right here, this is what a server would need to do if you're doing a chat system, is that you say serve, and you give it the function that gets called when a message is received, and then you handle it. And you give it the host name and the port number. And then likewise over here, this async IO get event loop, blah, 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 blah. You can think of this as boilerplate. This is just kind of crap that you need to do in order to make sure that this WebSocket server runs. So ideally they would have. Oh, sorry. There's a typo in here. I'm sorry, guys. This server loop and start server should be the same thing. I renamed server loop, but I didn't rename start server. Crap. Oh. Let's see. Server loop. Let's see if we can do a quick Photoshop job. Gray, white. There you go. Okay. Is that better?
I think like one of the challenges for me is like that I have to figure out which one is a built-in function from Python,
yeah. Okay.
and then like also like what's like built-in from the WebSocket package that we use.
Yeah. So let me retype this up in a different panel, and then we'll look at that. Okay. So if we look over here, oh, that was the client side. This is the server side. So in this case, everything should be fully on the screen. There should be nothing here where you have to like make something up like last time. So take a look at this and see if this is more readable. How are we feeling? All right. Don't feel too bad. Again, this stuff you will have in the scaffolding. Let's take a quick look at the connect thing and see if connect is any easier, and then we can come back to that one. So this is connect. This is if you're a client. Oh, there's chatmarina.com. This is if we're the chat client running on the phone or wherever, and we're connecting into the server. So take a look at this. See how comfortable this one feels.
I think I understand this one.
Yeah?
Yeah. So you're saying that, like at a high level, you're saying that, okay, get everybody to connect asynchronously to this chat.marina.com as a local host, and then you want to make sure everybody connects independently. So you make it an await statement so that you ensure that every person gets connected. And then you keep looping it until it's completed.
Yeah, so that's all good with one minor thing, that when we run this program, you should assume that it's just on one computer with one user for now. So I think right now it sounded like you were envisioning with many people in this program all at the same time. And you're right, async actually is very helpful for that case, but async is also helpful for, let's say, send message. Like every time I hit enter, if I say like, hello, how are you? Enter, good, enter. Every time I'm hitting enter, in my program, I might be calling some sort of async, send message function, right? And every time I hit enter, I don't want the screen to wait for the message to finish sending before I go on to do something else. So does that make sense so far?
Yeah.
Yeah. So in this case, in the case of Hello Socket, then basically, yeah, like this async thing is here. It's like, well, at least don't block the current program while you connect. So like if I have something else, like I might, I don't know, like I might down here, I might say the program is running, then input, what's your favorite color? Your fave color is color. So in this case, because Hello Socket and this connect are both async, then in this case the program is running and this what's your favorite color, these will both fire while the connection is still going on, right? While this is still connecting, and then it finishes connecting and then it says, hey, I connected, right? And that might happen at the same time as this is going on down here. So that's the main reason that we're using async, and it's not necessarily because we have like 100 people on my computer all trying to get in. Should I have made this a more of a real world example? Maybe I should have made this a real world example. Maybe here, username or a screen name. Is that a little bit better? Maybe? Not so much.
Yeah, it's just the loop to complete.
Yeah, like
It's this one?
Yeah, that's the part where.
Yeah.
Yeah. So. Is it just because once it gets the one-time connection, Python would just complete that task, but you just want to keep it running?
Yeah. Basically that's exactly right. Is that if we if we just had it like this, then I don't know if Python would actually let us complete the task. I don't think it would. Like, I think that by default, you need to say await hello socket to wait around and let it finish. So essentially, this event get loop run to complete blah blah blah. Essentially, it's like a fancy way to to make sure that we do get the answer out of this thing, but that also if we were awaiting, like if we were awaiting, then we couldn't say print hello. And if we used await, then we would never get the hello. But if we use run until complete, we get the hello and we can go on with our life, but we don't leave the program until this is done.
Mm-hmm.
Yeah, these are similar but different, guys. It's right here.
Yeah, like so the function of WebSocket.send. So what does that exactly do? Because I guess I'm just trying to figure out like does that line 6, does it actually will it print out when it's connected to the whole?
No, it doesn't. It doesn't print out on this computer. It sends that to the other computer. So you could say something like dear server, I connected, and am your biggest fan. That's your love letter to the chat server. And then you can send another thing. You could say I don't know. My user's screen name is blah. Or you can say that message equal to 124 or whatever, equal to hello. You can send whatever you want using WebSocket send.
Okay, so this is just something where you need, like, basically because you have a wait, it's just something that you want to send to everybody to make sure, like, for sure that you want to send, right?
Are you talking about why I'm using await and why I'm just not doing async? I think that in this case, all right. So let's come back to let's see. Okay. So in this case right here, I'm going to delete these lines. In this case, the WebSocket definitely sends our love letter to the server. In this case, this love letter may never get to the server.
Mm-hmm.
Do you see why?
Yeah.
Why?
Because you didn't put await, so you're not waiting for anything.
Yeah, and by default, Python just walks through the program, and if it gets to the end of the program, then you're done. Like if you say print hello world, then after that, oh, there's nothing here, so Python just terminates everything.
Mm-hmm.
It's like you kind of fall out of the bottom. Right? So in order to not fall out of the bottom, we can add this await statement that makes sure that this thing is done before we finish. Good so far?
Yeah.
Okay, so now if we come back to this event loop thing, and in this case, this event loop thing is essentially awaiting this WebSocket send, so we don't leave the program before it sends. Still good?
Mm-hmm. So right now, without the await statement, it'll just keep going and going until it actually connects, or until, so like nobody will, like it won't for sure, it won't wait until everything is sent. Like you won't know the progress, right? Because you don't have a wait.
Oh yes, you're right. Right now in this there's no indicator of how far along this is until other than the fact that the program will end when it's done.
Okay. Yeah.
That's the indicator, yeah.
Okay.
So anyway, it'll take a little practice to get 100% comfortable with this stuff. But if you guys understand this example here, that's like 90% of it. And then it's a slightly different version for the server. For the server, you say serve instead of connect, and then you give it this function that you run on every message. And then you'll notice that here, for the first one, we said run until complete. This other one, we say, oh, sorry. We say run forever. And essentially, this will basically just run, or actually, I'll call it server handler. Yeah, it's a little better. Say run forever, and then on every message that comes in, we run this function. Anyway, we unfortunately are running low on time, so let me jump back in the slides and just finish up the, yeah, as you see, we have the listen example, we have the connection example that we just looked at. Just a reminder, if you want to get input from the user, you use the input function. And today, we had a whirlwind tour through how the internet works. Look at the protocol stack, TCP, UDP, plenty of stuff on WebSockets, and I guess I forgot to write async await is a big thing right here. For homework, even though you'll have to turn it in without a next class, make a chat server where multiple users can connect and chat with each other. Each user must have a screen name, and you should be able to close the clients and server in any order. And I'll give you a scaffold after class. Bonus assignment. Extend your chat server to be a network shared whiteboard so you can draw in black and white. I guess you should. Start with just black and white. Use the decontour library, and I'll give you a scaffold for that as well. So the idea being that when you're building a chat system, it's actually not that different from building a shared drawing application, like a whiteboard. So I'll give you the scaffold so you can get up and running, but I think this is pretty neat. And then some discussion questions for you guys, or some thought-provoking questions. How do you know which user sent a message? How do you send a message to all your connected users? What should happen when a client disconnects or the server disconnects? Likewise with bonus assignment, how do you send your drawing data over the network? Actually, I'll ask you that right now. Does anyone have any ideas about how you might send drawing data for a whiteboard app? No? All right. Well, we'll leave that as open for you guys assignment. So any final questions as we are winding down? No? All right. Well, folks, sorry that we had to rush through the last couple of minutes, but thank you very much for joining me on this journey. I hope you have learned a thing or two about programming, and I hope you'll continue to program in the future. Please email me your assignments. I don't matter if they're 3 months late. I would love for you guys to all take a stab at the 7 assignments of the class. So let me know if you get stuck on anything. Otherwise, I will see you in the future. All right?
Thank you.
Thank you.
All right. Great. I'll see you later, man. Bye, guys.